Before we actually get into formulas for this exercise, 6K, the limiting sum, I encourage you just to have a bit of a think about what limiting sum might actually be referring to. And it's easier to look at some examples. You can see here that I've written out a sequence where r is equal to 2, for example, and we're starting at 10. So we've got the terms 10, 20, 40, 80, 160, 320. You can probably see that the terms are increasing fairly significantly now, and as we continued on, they would continue to get bigger and bigger. The limiting sum, if I was to add up the sum as we progress further, are we getting to a limit ever? Well, I guess you really have to consider an infinite number of terms, and in doing that you could see that, well, if all the terms are getting bigger and bigger, then the sum's getting bigger and bigger. The sum's going to infinity as, I guess, as our limit. So when r is equal to 2 or 3 or any number greater than 1, you don't have a specific limiting sum because it is infinity. On the other hand, when we have a GP and r is equal to a half, for example, well, we start off with 10, but this time our ratio is a half, so we get a 5. Then we get 5 on 2, which is 2.5. Then we get 1 1/4. And then we get, because all I'm doing here is multiplying everyone by a half. Then we get 5 on 8, a number just a bit over a half. 5 on 16, a tiny bit more than 1/4. Now, you can see that these terms are getting smaller and smaller and smaller. As your denominator gets bigger, your overall value gets smaller. So eventually our terms are so small they're almost insignificant, and we could almost say they were nothing. They were so small it was like adding on nothing. But what would our sum be? We've definitely got a 10 and a 5. We've got 15, a 2.5, 17.5, another 1, 18 and a bit. And do we push to over 19? And we're adding on little bits here. What you can probably imagine now is that, yes, we're getting up to 19, 18, 19, 20, but very quickly we're going to be almost adding on nothing. So as our terms n goes to infinity with an infinite number of terms, do we get a limiting sum? And the answer is yes, we do. Because the tiny little bit that you are going to add on is so insignificant, it's not going to really impact on the overall size of the sum. So that's what limiting sum is, and this only occurs when we have GPs, and it only occurs when the GP has a ratio that's a fraction, a proper fraction. So you could see here, back to the first example I showed you, it wasn't ever heading towards a particular value, unless of course you think of infinity as a value, and we don't. So you will get a limiting sum only when the common ratio of the GP is a number between -1 and 1. that is, it's a proper fraction. Or we could say the ratio is greater than -1, less than 1, or the absolute value of the ratio is less than 1. So what happens is that as n approaches infinity, r to the n, keeping in mind that r is a fraction, so we're making the denominator bigger and bigger, and when you make your denominator bigger and bigger, actually the value of the fraction becomes smaller and smaller, and we say that r to the n actually goes to 0. So what does that mean for our sum formula? So we need the formula in the format a times 1 minus r to the n over 1 minus r, because that's the formula we use when r is a proper fraction. So taking that formula, hopefully you can see that when n is going to infinity, the 1 minus r to the n goes to 1, because we've just said r to the n goes to nothing. So we get that the limiting sum as n goes to infinity of a times 1 minus r to the n actually is just a over 1 minus r. This bracket goes to 1. We've just shown that there. This then becomes known as our limiting sum calculation for a GP. So back to our example up here, where a was equal to 10, r is equal to 1/2, our limiting sum, our sum to infinity, as our number of terms got bigger and bigger, what did our sum actually become? Well, a is 10 over 1 minus simply 1/2. So that's 10 divided by 1/2, divide by a fraction, multiply by 2. Our sum is 20. Now when we did some rough calculations here, we knew that we were getting over 18, we got to 19, we were still adding on a little bit and wondered, would we get to 20 or would we go over 20? Well, here's the answer. This calculation actually says that the limiting sum of that GP would actually be 20. You may not actually get there, but you get so close that well, you won't actually get to a limiting sum, but you'll get very, very close. And so this becomes really important, and it's on the reference sheet. So again, use your reference sheet when you're doing every question out of the textbook, because then it becomes automatic that you see a question in the exam and you go to your reference sheet. You must practice this. This is, again, just a good habit to get into. There are some different notations for indicating the limiting sum of a GP. It may be written with limit written as LIM, as n goes to infinity of the sum of n terms. It may be just written as S infinity, or you might see the worded description, find the value that the sum to infinity converges to. So just be aware of that. I'll stop the video now and do the examples separately.